Good afternoon, everyone. My name is Abrar Sheikh, and in a moment, you'll also meet my colleague, Alex Yang. We both work on the RayServe team within Anyscale. And today, we'll be talking about all the advancements we've made in terms of scalability, performance, and flexibility of the framework within the past 1 year. We'll start off by talking about what RayServe is as a project, why you should consider using it. From there, I'll talk about some of the improvements we've made in terms of improving the flexibility of the framework. Then Alex is going to talk about the performance characteristics of RayServe and contrast that with our Anyscale runtime. And then finally, we'll do a demo of like what's coming in the future in terms of multi-cloud services support within Anyscale. Anyscale helps accelerates user journey from taking a model in development to production. It helps deploy and scale any AI workload on any cloud, all under a single platform. At its core, Anyscale is built on top of Anyscale runtime, which is also commonly known as like Ray in the open source community. RayServe is one of the libraries within Anyscale runtime. It is a production-ready AI inference engine built for scale. The problem RayServe tries to solve is as follows. Many teams can train a model, but actually deploying them in production is often quite challenging. Serve tries to solve this last mile delivery problem of meeting where the users are in their ecosystem and in the phase of building their model. Right? Once you train a model, Serve makes it really easy to take the model from the same ecosystem and deploy it into production. No need to repackage the model as a microservice in order to ship it to your customers. Next, in order to run an AI inference engine in production at scale requires setting up multiple complex systems. As an example, to do autoscaling needs configuring Kubernetes HPA. To do request batching needs setting up custom middlewares and fast API. Or to do model composition, users need to do service discovery setup in their Kubernetes ecosystem. Or to do request scheduling and routing needs setting up a reverse proxy. Serve consumes all of this complexity away from user and exposes a clean set of APIs that they're already familiar with. Today's AI inference workloads are moving away from single API, single model paradigm to a single API needing inferences from like multiple models or a chain of models. Serve exposes a clean API for expressing model composition, which are intuitive and easy for a developer to understand. Finally, Serve comes out of the box with mature concurrency model, error handling, back pressure, retry, error code handling, and much more. Also integrates seamlessly with Kubernetes and Anyscale in order to facilitate controlled deployments or cluster orchestration. So I think for all of these reasons, you'll find Serve to be much more competitive compared to some of the other products in the market. At its core, the team really tries to strike a good balance between these three vectors. As you'll see in today's presentation, that we've made significant improvement in areas of flexibility and performance, but at the same time, every time we try to add a new feature into the framework, we ensure that we introduce least amount of new concepts that the users of the library need to learn in order to get started. Either you are starting new or someone who has experience using RayServe in the past, the API seem very natural and not daunting at all. In the next section, I'm going to talk about some of the new inference capability that we've added in Serve, and we will start off by talking about support for async inference. Fano AI is a language-based AI company from Hong Kong. Their clients are other enterprises that manage large amount of call center audio data. Their AI inference workload is, their typical workload is a large amount of audio data gets passed through a language model to generate analytics. And Fano maintains the proprietary models and also the inference engine. The inference engine that they have built is built on top of RayServe. But some key characteristics about their workflow is that since the audio files are quite large, the inference requests on them can span over multiple minutes. So for that amount of time, it's not preferable to block user request. Instead, Fano was looking for a solution where the request can be handed off to a background worker, and the client can poll the result of the request in the future. At the same time, what was preferable was to be able to query the status of the task, retry them if the task has failed, pause and resume tasks as needed, and also ensure that the task eventually gets executed, despite the cluster health or service deployment and all of that stuff. So in the past 6 months, the Serve team has implemented native support for async inference inside RayServe. Let's try to understand how Fano built their AI workload using the async inference feature within Serve. They have a large audio file. Client first uploads that to S3, then makes a request to the ingress deployment using the reference to the S3 file. From here on, the ingress deployment enqueues that task in the Redis queue and then immediately sends a response to the client. At this point, client has a reference to the task, but the API request has been terminated. So they don't need to block on the request getting completed. But they can use the reference to query the status of the task in the future. From here, a pool of Celery workers dequeue the task from the Redis queue and utilize the existing deployments within the Serve application to complete the user request. This paradigm is not new, but what sets the RayServe's integration with async inference apart is that the pool of Celery workers are fully managed by Serve internally as a deployment, which means these Celery workers have access to the existing RayServe deployments. They can, and the life cycle of these Celery workers are fully managed by Serve deployments, in addition to auto-scaling them based on the number of outstanding tasks in the Redis queue. In the specific example, I used Celery and Redis as the task processor and result backend, but that's not a hard requirement. Users can extend their own task processors and use different message brokers as they wish. In order to use async inference in your application, you first have to create a config object which has a reference to the queue name, a reference to the message broker, and an optional reference to a result backend. Then create an object of type adapter and use that adapter object to either enqueue the task in the queue or query its status. Finally, users have to define a task processor consumer deployment, task consumer deployment, which is a special type of deployment responsible for managing the life cycle of task processor in the previous example, which was Celery, and also contains instruction on how to handle individual tasks. The applications of async inference, I believe, is far beyond the audio processing example I provided before. I've seen customers use it for video processing, decoding tasks, or even processing large amount of text data to generate embeddings. Next, I'm going to talk about support for custom request routing within RayServe. The default routing algorithm that ships with Serve is called Power of 2 scheduler. And the way it works is it picks 2 replicas at random and then sends the request to the one with least load. This algorithm is great because it tries to optimize the difference between your replica with the maximal load and your average set of replicas. So it works great for most routing needs. But let's contrast this with a use case in LLM inference, where if you have an inference request for a turnstile type chatbot system, it's preferable to route the request to a replica that has seen some part of the prompt prefix before. This ensures that we can leverage the warm KV cache on that replica. It ensures that we have high GPU utilization and also ensures that we have low latency on the request. With the support for custom request routing in Reserve, users can now express routing policies that are as complex as this. If we look at a typical request from within the Reserve, routing decisions are made in exactly two places. One is at the ingress layer or at the proxy. Second is between inter-deployment communication. And by specifying a custom routing algorithm, we can influence the routing decisions at both those places. And at the same time, users have the ability to specify the routing policy for individual deployments, which means users can now express write complex application where each deployment has a different routing policy. In order to use custom request routing in Serve, users first have to implement a routing policy class extending from request router and implement a function called choose replicas. This function takes in a candidate set of replicas that are injected by the Serve framework automatically, and then it's expected to return a ranked set of replicas, which means, and Serve will try to send the request to the replica in order of ranked replica. And then finally, users have to associate this routing policy with a deployment. This instructs the framework to override the default policy and use the user-provided custom policy. In order to make it easy for users to write their policy, we also ship the library with set of mixins that users can use. As an example, the locality mixin ensures that we try replicas on the same node before trying replicas on outside of the nodes or outside of the availability zone. Next, I'm going to talk about support for custom autoscaling in Reserve. Huawei uses Reserve for their LLM inference pipeline. It's a typical Serve application with 3 deployments: a pre-processing stage, LLM inference stage, and a post-processing stage. Nothing too particular about this. What they found was the autoscaling functionality within Reserve was quite limiting. The way it works currently is we look at the target number of requests set by the user on a deployment. Serve internally computes the number of ongoing requests and then decides the target set of replicas for each deployment by looking at the relative difference between those two quantities. What Huawei wanted to do was express a autoscaling policy which was a bit more complicated, where they wanted to make decisions based on custom metrics emitted from within the Serve application, for one. Second, they wanted to write a policy that could take decisions across all deployments, not just for individual deployments, which was the case before. So for the past 3 months, Huawei and Anyscale have been working in collaboration in order to add support for custom autoscaling within Reserve. This is one of the more successful open source industry collaborations we've had, so I'm really happy that we are shipping this feature. The way this works is replicas within each deployment have the ability to now emit custom metrics. Serve ensures that these metrics get transported to the controller and makes them available for in the context of a autoscaling policy. These metrics are regularly pulled from replica by the framework, so users don't have to do anything special. Serve enriches the custom metrics with its own metrics that are tracked by the framework, like number of queued requests and number of ongoing requests. And we also now have the ability to run a custom policy function as part of the serve controller's control loop. Users can specify a policy not just at a deployment level, but also can write a policy that spans across multiple deployments at a application level. In order to use custom autoscaling within RayServe, the first thing users have to do is implement a function called record autoscaling stats in their deployment. This function is expected to return a dictionary of metrics. And again, this is completely controlled by the user. They can choose to populate this dictionary the way they want to. Serve will periodically poll this function and transfer the metrics from replica to controller at some regular cadence. Then users need to define a custom autoscaling function. This function gets executed as part of the control loop. It takes in autoscaling context object as input and is expected to return a target number of replicas as output as a decision vector. The autoscaling context object is a feature-rich object made available to the writers of the policy. It contains the custom metrics that users emitted. It also contains the metrics tracked by serve internally. And finally, users have to associate this policy with their serve config, which tells the framework to disregard the default policy and use the one provided by the user. The application of custom autoscaling is enormous. Users can define policies such that we can scale up replica during a specific time of the day or scale them down to 0 during night, right? To much more complicated policies that depend on predictive autoscaling and forecasting models to SLA-driven autoscaling, right? As an example, I think in the previous slide I talked about how the celery workers are autoscaled based on the number of outstanding tasks in the queue. That implementation was possible because of the support for custom autoscaling in Serve. Next, Alex is going to talk about some of the performance improvements we've made in Serve.
Thank you, Abrar. So we talked about the philosophy of RayServe, and we've seen the many new features in making Serve a flexible serving framework. Now let's talk about scalability. So when we think about model serving at scale, efficiency is super important, not just for reducing infra costs, but also for the end user experience and overall system reliability. Now, even though many services running large GenAI models don't necessarily need to run at very high throughputs, there's still tons of models and applications running on smaller to medium-sized models where you want minimal serving framework overhead to maximize your concurrency and GPU utilization. So as a result, over the last year, we spent a lot of effort optimizing RayServe to make it more efficient, especially when running on Anyscale. And to illustrate this point, we set up a simple benchmark where we compare RayServe against Anyscale runtime. So we benchmarked a generic recommendation system application running DLRM with about 166 million parameters running on GPU with serve dynamic batching enabled to maximize your GPU efficiency. And the rest of this setup is pretty simple. There's an ingress deployment that's handling incoming requests, doing some pre-processing, and then forwarding the request to the GPU ranker deployment. This is a pretty common setup that you see in many real-world inference pipelines. So in our benchmark, we ran load tests at various user concurrencies and varying number of ranker replicas to compare throughput and latency between Ray open source and Anyscale runtime. So these are the results for Ray open source in this benchmark. On the left, you see peak RPS at 1, 2, and 4 number of GPU replicas. On the right, you see the corresponding median latency at these throughputs. So Ray open source reached peak RPS at 75, 100, and 100 users for 1, 2, and 4 GPU replicas respectively. And if you look at the graph on the left, see that when increasing from 1 to 2 number of GPU replicas, peak throughput increases by about 50%. But when you increase from 2 to 4, it only slightly improves. So clearly, we're not seeing like the same scaling factor increase in throughput as we scale the number of GPU replicas. However, when running the benchmark on Anyscale runtime, the results are completely different. At one number of GPU replica, Anyscale runtime is able to serve 3 times the amount of throughput compared to Ray open source. And at 4 GPU replicas, Anyscale runtime is serving 6,300 requests per second of a recommendation system application, which is 7 times over that of open source. And Anyscale runtime reached the peak RPS at 200, 400, and 750 users. So we're seeing that near linear scaling increase in throughput as we scale up the number of GPU replicas. And we're able to achieve this without sacrificing any latency at all. And in fact, the latency is actually better. If you'd like to try this out for yourself, you can follow that link at the bottom left, where we have all the code and setup required for you to try it. So what's really driving these improvements? A lot of it comes down to optimizations at the serve actor level. We've reduced a lot of the overhead of operations not running on the critical path so that the serving framework can actually spend more CPU cycles actually processing the request. One of the biggest improvements we made in this area is providing the option in serve to combine serve's multiple threads and event loops into a single one instead of many. So this is a huge performance lever because it reduces context switching and the overhead from managing multiple async event loops. We basically wanted to keep serve's mental models simple while providing power users the ability to turn off these safety guardrails built into serve when they want to maximize their performance. We also more aggressively buffered logging and metrics to reduce I/O overhead and optimized tracing such that observability comes with minimal performance penalty. And lastly, since routing is at the core of all serve workloads, we made a lot of work to optimize the routing layer to reduce any latency introduced there. The second class of optimizations is in the communication layer. We're able to increase the total object transfer bandwidth and just reduce the overall communication overhead between the serve actors. So these are just some of the efficiency work that we've done in the past year, and there's still a lot more that we plan to do to make both open source Ray serve and Anyscale runtime more performant. For the final part of this presentation, I'd like to introduce Anyscale Multicloud Services, which is a new feature coming to Anyscale that we'll demo today. To give a bit of context, when running AI workloads, we face 3 main problems today. The first is that GPUs are extremely scarce, especially when you run in a single region and constrained within a single cloud provider. The second is that running a service in a single region puts your service at risk when a region goes down, and regions go down for random reasons that we can't control, like natural disasters or cloud provider infra bugs. Lastly, when we're finally operating in a multi-cloud environment, it becomes more difficult to manage and prone to error. So the solution we built at Anyscale is an Anyscale service, a single one that seamlessly spans multiple clouds and regions. This also comes with all the benefits of Anyscale services today, like coordinated rollouts, rollbacks, managed load balancers across all your clouds and regions, and many other things. So before we jump to the demo, I'll just give a brief overview of what we're going to see. We're first going to launch a multi-cloud Anyscale service in both, and the clusters are going to operate in both AWS and Google Cloud in 2 separate regions. Next, we're going to spin up a few clients that are going to send continuous traffic to our service. The traffic is going to be split between the AWS cluster and the Google Cloud cluster, and these weights are dynamically configured by the Anyscale control plane depending on the hardware availability in the cloud provider's region. Finally, we're going to simulate an AWS cluster failure and watch as the traffic begins to shift away from the AWS cluster into the Google Cloud cluster. And we'll also see that the cluster running in Google Cloud will upscale to support the influx in demand. So here is a Anyscale multi-cloud that we've created to support both AWS and GCP. Next, we'll create an Anyscale service running in this Anyscale multi-cloud. As you can see, the interface of doing so is exactly the same as you start any other Anyscale service. We'll go to the console and click into the services UI. And in the middle of the console, we can see that the service is in fact starting 2 clusters, one in each cloud provider, with dynamic weights on the right. From the logs, we can see that the 2 clusters are starting instead of 1. So the clusters will become active, and then we can see that the served deployments are running and healthy in each of the 2 clusters. And in the logs, we can check that the DNS record for our service hostname is being correctly configured in Route 53. And now our service is in a running state, so we'll start the load test that will send continuous traffic to our Anyscale multi-cloud service. So as traffic ramps up, we can see that the serve application is upscaling its replicas in each cluster, and the clusters are also upscaling their worker nodes to support the traffic. In this Grafana dashboard, we have RPS at the top, active nodes, and then replicas per each cluster. The green is for AWS, yellow is for Google Cloud. And we see that the traffic is being split proportionally based on the dynamic weights that were configured. And as traffic is increasing, we can see that the clusters and serve applications are continuing to upscale. Now we'll wait for the traffic to stabilize. Now it's stabilized. Off screen, we simulated an AWS cluster failure, and immediately we see the green line begin to drop, and the yellow line showing Google Cloud Cluster RPS begin to increase. And in the console, we see that Google Cloud Cluster is beginning to upscale its nodes to support the influx in demand. So as traffic is being shifted from AWS to Google Cloud, this cluster running in Google Cloud is going to upscale to match the autoscaling policy that we set in the service config. As you can see, the active nodes and replicas per cluster were increasing. Now that traffic has stabilized, autoscaling behavior is also going away. So we'll give this a second to fully stabilize, and then we'll be able to check the request latency of our application and see that it stayed completely flat throughout the entire experiment, even through the cluster failure event. Oops. So this is just one of the many benefits of running in an Anyscale multi-cloud service. If you want to learn more about multi-cloud and how Anyscale Infra intelligently manages all the resources across all your clouds and regions, I highly encourage you to check out Janet and Simran's breakout session talk later today at 4 p.m., I think, where they'll dive deeper into this topic. So to wrap things up, we'll go back to this diagram. We've seen the many new features in improving flexibility and performance in RayServe, all the while keeping the ease of use and making RayServe a pleasant experience for developers. So if you thought any of this stuff was interesting and you'd like to try it out for yourself, you can go ahead and scan this QR code to link and try out it on the Anyscale platform for free with $100. Thank you. Are we good on time? There's like 20 seconds left.
We can do a little Q&A. Anybody else?
Abrar and I will be around if you guys have any questions. But yeah, thank you.